Greetings to all my dear viewers. Today we are going to focus on a technology that is becoming the center of attention in the society as a result of technological advancements over the years. The technology that is currently emerging as one of the greatest technological revolutions of times is none other than AI. AI is turning out to be a powerful incantation that is being chanted among many in recent times. AI has substantial number of users across various sectors ranging from agriculture to healthcare that are crucial in terms of a better livelihood for the individuals in the society. Trustable sources state that the agricultural sectors in the society have significantly developed and nourished with the use of AI. The sources also state that AI has helped farmers identify areas of the field that needs irrigation, fertilization, pesticide treatments, or increasing yield. Agronomists use AI to conduct research and development. AI has been used to predict the ripening time for crops such as tomatoes, monitor soil moisture, operate agricultural robots, conduct predictive analytics, classify livestock pig call emotions, automate greenhouses, detect diseases and pests, and save water. AI in healthcare is often used for classification to evaluate a CT scan or electrocardiogram or to identify high-risk patients for population health. AI is helping with the high-cost problem of dosing. In 2016, a study reported that an AI-derived formula derived the proper dose of immunosuppressant drugs to give to transplant patients. For certain disorders, AI algorithms can assist with diagnosis, recommended treatments, outcome prediction, and patient progress tracking. AI technologies can revolutionize cancer treatments by helping oncologists through providing them with personalized treatment recommendations for their patients. They can analyze patient data such as medical history, lab results, and imaging scans using machine learning algorithms and then cross-reference this data with vast amounts of clinical trial information and medical research. Based on this analysis, they can generate a ranked list of treatment options that are tailored to each patient's unique medical profile. This helps oncologists make more informed decisions about which treatments to pursue, potentially improving patients' outcomes and reducing treatment-related side effects. Additionally, they can help oncologists stay up to date with the latest advancements in cancer research by providing access to the latest scientific publications and clinical trial data. One study demonstrated surgery with an autonomous robot assisted by AI-based applications. It was conducted by researchers at Children's National Hospital in Washington, D.C. and Johns Hopkins University in Baltimore, Maryland. They employed the robot called STAR, Smart Tissue Autonomous Robot, to perform bowel surgery on pigs. The robot was able to successfully stitch together the pig's bowel with greater precision and consistency than a human surgeon. The robot used computer vision and machine learning algorithms to identify tissue and other anatomical structures, and it also employed force sensing to ensure that it did not damage any of the delicate tissues. AI is also playing a vital role in the testing and development of pharmaceutical drugs. AI is being increasingly used to develop non-animal alternatives to the testing procedure of pharmaceutical drugs, and some of the non-animal alternatives to the testing procedures involves in silico models, organ-on-a-chip models, high-throughput screening, and computational simulations. The term in silico refers to computational models that investigate pharmacological hypotheses using methods such as databases, data analysis tools, data mining, homology models, machine learning, pharmacopause, quantitative structure activity, relationships, and network analysis tools. One important application of in silico modeling in drug testing is virtual screening, where large databases of compounds are screened to identify those with the highest likelihood of interacting with a target molecule or protein. This can help researchers narrow down the potential drug candidates for further testing. Virtual screening can be categorized into two types, namely ligand-based virtual screening (LBVS) and structure-based virtual screening (SBVS). Molecular docking is a conventional structure-based virtual screening method that optimizes the orientation of a ligand and a drug target. However, when the three-dimensional structure of the drug target is not available, ligand-based virtual screening should be the first choice for drug discovery. For ligand-based virtual screening, fingerprints with high dimension of features are firstly generated to describe the chemical characteristics of ligands, and then similarity searching or machine learning approaches are applied for screening in high-dimensional data. In similarity searching, the fingerprints of a large number of compounds are compared to the fingerprint of a known ligand that binds to the target protein. If the fingerprints are similar enough, it is assumed that the compounds will also bind to the protein. By comparing the fingerprints of large numbers of compounds to that of a known ligand, similarity searching can identify potential new ligands for the target protein. In machine learning approaches, a model or algorithm is trained using a set of known ligands and their corresponding molecular fingerprints. During training, the algorithm learns to recognize patterns and relationships between the features in the fingerprint and the ability of the ligand to bind to the target protein. This is done by minimizing an objective function that quantifies the difference between the predicted binding affinity of the ligand and its actual binding affinity. Once the model is trained, it can be used to predict the binding affinity of new compounds by calculating their fingerprints and comparing them to the fingerprints of the known ligands in the training set. The model assigns a score or probability to each new compound, indicating the likelihood that it will bind to the target protein. Compounds with higher scores are considered more promising candidates for further testing. Overall, ligand-based virtual screening is a powerful tool in drug discovery that can help identify promising drug candidates quickly and efficiently. In silico modeling also allows for the prediction of drug toxicity and pharmacokinetics, which can help to reduce the cost and time associated with traditional in vitro and in vivo testing. One approach to in silico modeling for predicting drug toxicity is quantitative structure activity relationship (QSAR) modeling. QSAR models relate molecular structures and properties to biological activity, such as drug toxicity. Molecular descriptors are numerical values that describe different structural and chemical properties of molecules. These descriptors can be used to develop QSAR models. Examples of molecular descriptors include molecular weight, number of hydrogen bond donors, and number of hydrogen bond acceptors. Selecting the most informative descriptors for developing a QSAR model can be facilitated through the process of feature selection. The goal of feature selection is to identify a subset of descriptors that are most important for predicting toxicity. Once a set of molecular descriptors has been selected, statistical analysis can be used to develop a QSAR model. This involves using various statistical techniques such as regression analysis to relate the selected descriptors to the biological activity being modeled. The resulting QSAR model can then be used to predict the toxicity of new compounds. For example, let's say we want to predict the toxicity of a new drug. We could develop a QSAR model using molecular descriptors such as molecular weight, number of hydrogen bond donors, and number of hydrogen bond acceptors. We would have to also use statistical techniques in the process of developing QSAR models, and the purpose of using statistical techniques in the process is to relate the molecular descriptors to toxicity. Once the model is developed, we could use it to predict the toxicity of other drugs with similar molecular structures. Overall, QSAR modeling is a powerful tool for predicting the properties of chemicals and is widely used in drug discovery and toxicology research. In silico modeling also allows for the prediction of pharmacokinetics by simulating how drugs are absorbed, distributed, metabolized, and eliminated in the body. These processes are influenced by various factors such as drug properties, patient characteristics, and dosing regimens, which can be modeled using computational methods. For example, physiologically based pharmacokinetic PBPK modeling can be used to simulate drug distribution in various tissues and organs, which can help to predict drug concentrations and exposure levels. By using in silico modeling to predict pharmacokinetics, researchers can optimize drug dosing regimens and identify potential drug-drug interactions, ultimately leading to safer and more effective drugs. In addition to predicting drug toxicity and pharmacokinetics, in silico modeling can also be used to optimize drug design, identify new drug targets, and reduce the time and cost associated with traditional drug development methods. By leveraging computational methods, researchers can gain deeper insights into drug behavior and interaction with the body, leading to the development of safer and more effective drugs for patients. Overall, in silico modeling is a valuable tool in drug development that allows researchers to simulate and predict various aspects of drug behavior and interaction with the body. Now, the non-animal alternative to the testing procedure of pharmaceutical drugs is the organ-on-a-chip modeling. Cord blood stem cells, such as umbilical cords and placenta, are a particularly useful source of cells for organ-on-a-chip models, as they can be readily expanded and differentiated into the specific cell types needed for these models. Cord blood stem cells are a valuable source of cells for tissue engineering and can be used to create a variety of different tissues, including liver, lung, heart, and kidney tissues. Organ-on-a-chip OOAC is a novel in vitro microscale biomimetic platform that helps in reproducing the physiological environment of human organs. The system uses microfabrication techniques to create a more realistic physiological environment of human organs. One common microfabrication technique used by the system is soft lithography, which involves using a soft elastomeric material to create microstructures on the chip. Another technique is microfluidics, which involves the precise control of fluid flow within microchannels on the chip. In addition to these techniques, other microfabrication techniques such as microelectromechanical systems, MEMS, and nanotechnology can also be used. These techniques allow for the fabrications of complex structures and the incorporations of sensors and other electronic components into the organ on a chip device. Overall, the use of microfabrication techniques has enabled the development of organ on a chip technology, which has great potential for advancing drug development and disease modeling. Organ on a chip models are typically made up of a combination of living cells which are cultured in the microfluidic device that mimics the physiological environment of the organ being modeled. The miniature models of organ on a chip mimic the structure and function of human organs, allowing researchers to study the effects of drugs and toxins without using animals. Organs on a chip models typically contain a combination of living cells that are organized and cultured in a microfluidic device to simulate the structure and function of human organs rather than the actual organs themselves. The microfabrication techniques used to create these devices, such as photolithography and soft lithography, allow researchers to precisely control the spatial arrangement and mechanical properties of the cells within the chip, creating a more realistic physiological environment than that can be achieved using traditional in vitro models. For example, a liver on a chip model might contain hepatocytes that are the main functional cells of the liver, as well as other supporting cells and tissues that are all cultured together in a microfluidic channel that allows researchers to control the flow of nutrients, drugs, and other compounds through the system. By creating more realistic models of human organs, organ on a chip technology has the potential to revolutionize drug development and personalized medicine. Organs on a chip models can help develop personalized medicine by allowing for patient-specific drug testing and treatment. Organs on chips are systems containing engineered or natural miniature tissues grown inside microfluidic chips. To better mimic human physiology, the chips are designed to control cell microenvironments and maintain tissue-specific functions. These chips contain tiny channels and chambers that are lined with living cells and replicate the physiological and mechanical functions of organs or tissues. These models are loaded with living cells that are arranged in a way that replicates the structure and function of the organ being studied. To perform drug testing, scientists introduce the drug to the cells and monitor their response using various sensors. By doing so, they can observe how the drug affects the cells and how the cells respond to the drug in real time. This method allows researchers to observe the effects of the drug on the organ in a more realistic and detailed manner than traditional animal testing. There are various types of sensors that can be used during drug testing by organs on a chip. Some of the commonly used electrochemical and microfluidic sensors include pressure sensors, temperature sensors, pH sensors, and oxygen sensors. These sensors help to monitor the physiological conditions of the cells on the chip and provide real-time feedback on the effects of the drug under test. Additionally, some organs on a chip also use imaging sensors such as microscopes or cameras to visualize the cells and tissues on the chip and analyze their response to the drug being tested. Organs on a chip technology is based on the idea that by recreating the microenvironment of living organs in vitro, researchers can better understand their functions, diseases, and drug responses. These chips are usually made of transparent materials such as glass or plastic and are small enough to fit in the palm of your hand. The channels and chambers in the chip are then lined with living cells such as human tissue that are designed to replicate the specific organ or tissue that the chip is meant to mimic. With the help of microfluidics, the chip can even simulate the blood flow, mechanical forces, and other environmental factors that the specific organ experiences in the human body. By using this technology, researchers can study the effects of drugs, toxins, and disease on the specific organ or tissue in a controlled and realistic manner, which can help improve drug development and reduce the need for animal testing. AI can help researchers analyze the data produced by organ on a chip experiments, identify patterns, and predict outcomes more efficiently and accurately. While in vitro models and organs on a chip have shown great promise in replicating certain aspects of organ physiology, they are not yet able to capture the entire range of functions of a complex organ or a whole body. These models are designed to mimic specific aspects of an organ's function, such as drug metabolism or the response to specific stimuli, but they cannot yet replace the complexity of a fully functional organ or body. However, they can provide valuable insights into the behavior of individual cells or small groups of cells, which can help researchers better understand the processes that underlie disease and develop more effective treatments. Overall, organs on a chip models offer a more effective and efficient way to test drugs, which can potentially lead to fewer side effects and better drug development. High-throughput screening is another non-animal alternative to the testing procedure of pharmaceutical drugs. The first step in this process is to prepare a library of compounds which can be synthesized or obtained from commercial or academic sources. The compounds are then loaded into microtiter plates, which are placed in robotic workstations equipped with automated pipetting devices and cameras. Machine learning algorithms are then used to analyze the data collected from the assays. These algorithms can be trained to recognize patterns in the data that correspond to specific types of biological activity, such as enzyme inhibition or receptor binding. To perform the actual screening, the robot dispenses small amounts of test compound into each well of the microtiter plate, along with the target molecule and any other necessary reagents. The plate is then incubated for a specific amount of time, after which the robot adds a detection reagent that produces a signal in proportion to the amount of target molecule bound by the test compound. The robot then reads the signal from each well using the imaging software, which collects data such as fluorescence intensity, absorbance, or luminance. This data is then fed into the machine learning algorithms, which analyze it to identify compounds that show promising activity. The most promising compounds identified by the machine learning algorithms can then be further tested in more complex assays to confirm their activity and assess their potential as drug candidates. Overall, HTS is a powerful tool that allows scientists to quickly identify potential drug candidates from large compound libraries, ultimately helping to accelerate the drug discovery process. Computational simulations is another non-animal alternative to the testing procedure of pharmaceutical drugs. Computational simulations play a crucial role in drug testing by allowing researchers to predict how a potential drug will interact with the human body without actually having to conduct clinical drug trials. One important type of computational simulation used in drug testing is molecular dynamic simulations. Molecular dynamic simulations play a critical role in drug testing by allowing researchers to predict how drugs will interact with biological systems at the molecular level. This information can help identify potential drug candidates and optimize their properties before they are tested in vivo. Molecular dynamic simulations use mathematical models to simulate the motion of atoms and molecules over time. This simulation can provide insight into how drugs interact with biological targets such as proteins or nucleic acids by allowing researchers to visualize the drug-target interactions in real time. They can also be used to predict the stability and binding affinity of drug candidates, which can help optimize their properties and efficacy. Molecular dynamic simulations are based on the laws of classical mechanics, and the behavior of atoms and molecules is represented by solving the equations of motion. In the case of drug-target interactions, the simulation would involve modeling the target molecule, which is often a protein, and the ligand or a drug molecule as collections of atoms connected by interatomic forces. These forces are typically described by mathematical models called force fields, which are parameterized based on experimental data. Once the force field has been defined, the simulation can be initiated by specifying the initial positions and velocities of all the atoms in the system. The simulation then proceeds by numerically integrating the equations of motion for each atom, which updates their positions and velocities at each time step. As the simulation proceeds, the drug molecule will interact with the target molecule in a dynamic and fluctuating environment. The simulation will capture these interactions and allow researchers to analyze the behavior of the protein-ligand complex over time. By analyzing the trajectory of the simulation, researchers can extract a variety of information about the interactions between the drug and the target. For example, they can calculate the binding energy of the complex, identify key amino acid residues that interact with the drug, and analyze the dynamic behavior of the complex to identify potential drug binding pockets. Furthermore, molecular dynamic simulations can be used to study the effects of mutations or other genetic variations on drug-target interactions. This information can be used to develop personalized drug therapies that are tailored to an individual's genetic profile. In addition, molecular dynamic simulations allow researchers to explore the complex interactions between drugs and cell membranes, helping to predict the potential for drug-induced membrane disruption and toxicity. By simulating the interactions between drugs and lipid bilayers, researchers can identify potential off-target effects and assess the drug's ability to cross biological barriers such as blood-brain barrier. Molecular dynamics simulations can help predict the potential side effects of drugs on other biological molecules beyond their intended target. By simulating the interactions of drugs with various biological molecules, researchers can identify potential toxicities and modify the drug to reduce or eliminate them. Additionally, molecular dynamic simulations can provide a better understanding of how drugs are metabolized in the body. Molecular dynamic simulation can provide a better understanding of how drugs are metabolized in the body by simulating the interactions between drug molecules and the enzymes that metabolize them. Enzymes are proteins that catalyze the chemical reactions involved in drug metabolism, and their activity can have a significant impact on the efficacy and toxicity of a drug. To simulate drug metabolism, researchers can model the drug molecule along with the enzyme in a molecular dynamic simulation. The simulation would involve specifying the initial positions and velocities of all the atoms in the system and then numerically integrating the equations of motion for each atom over time. As the simulation proceeds, the drug molecule will bind to the enzyme and undergo chemical transformations that result in metabolites. The simulations can capture the details of this interaction, including the atomic level mechanisms that drive the catalytic activity of the enzyme and the structural changes that occur during the reaction. By analyzing the trajectory of the simulation, researchers can gain insights into the factors that affect drug metabolism, such as the binding affinity of the drug for the enzyme, the rate of chemical reaction, and the stability of the intermediate and final products. This information can help researchers design more effective drugs that are less likely to be metabolized in undesirable ways. Molecular dynamic simulation can also be used to study the effect of genetic mutations on drug metabolism. For example, a mutation in a gene that codes for an enzyme involved in drug metabolism can alter its activity and affect the pharmacokinetics of a drug. Simulations of mutant enzymes can provide insight into the structural and dynamic changes that lead to altered function and help guide the development of personalized medicine. Drug toxicities can be evaluated in molecular dynamics simulations by modeling the drug molecule along with its targets and simulating their interactions over time. Toxicities can arise from a variety of factors such as off-target binding, adverse drug reactions, and toxicity resulting from drug metabolism. To evaluate drug toxicities, researchers can use molecular dynamic simulations to predict the binding affinities of the drug to its targets, including both on-target and off-target interactions. The simulations can also provide information on the structural and dynamic changes that occur upon drug binding, allowing researchers to identify potential toxicities that are related to changes in protein conformation or stability. In addition, molecular dynamic simulations can be used to simulate drug metabolism and predict the toxicity of the resulting metabolites. This can include simulations of the enzyme catalyzed reactions involved in drug metabolism, as well as simulations of the interactions between the metabolites and their targets. By analyzing the trajectory of the simulation, researchers can identify potential toxicities such as the formation of reactive metabolites or the inhibition of important cellular processes. Molecular dynamic simulation can also be used to evaluate the impact of environmental factors on drug toxicity. For example, simulations can predict the effect of pH, temperature, and ionic strength on drug binding and metabolism, which can be important factors in determining drug toxicity. Overall, molecular dynamic simulations are a versatile tool that can help accelerate drug discovery and development process, as well as provide a deep understanding of biological systems at the molecular level. Another important type of simulation used in drug testing is computer-aided drug design. In this approach, researchers use simulation tools to predict the best molecular structure for a new drug based on its desired activity as well as its safety and other pharmacological properties. This approach allows researchers to optimize a drug candidate for a specific target such as a disease protein or enzyme before actually synthesizing and testing the drug in the lab. Overall, computational simulations play a critical role in drug testing by providing a cost-effective and safe alternative to animal testing. They allow researchers to make more informed decisions about which drugs to pursue and how to optimize those drugs for maximum safety and efficacy. AI is also playing a vital role in the education sector as well. It provides personalized learning experiences for every student. It helps students learn at their own pace and cater to their individual learning styles. With personalized learning, students can focus on areas they need to work on and get the support they need to succeed. AI helps adapt lessons to the individual learning needs of students, which can help reduce stress caused by feeling overwhelmed or lost. AI-powered intelligent tutoring systems can provide students with immediate feedback and assistance, helping them improve their problem-solving skills and achieve better grades. AI can also be used to foster creativity in students by providing them with new and innovative ways to express themselves and explore their interests. AI helps students manage their time better by automating mundane tasks like scheduling and reminders, allowing them to focus on their studies and other activities. By analyzing student performance and behavior, AI can predict areas where students may struggle and provide early intervention, reducing stress and frustration. AI can also be used to provide mental health support to students. Chatbots or virtual assistants can provide students with support, advice, and resources on mental health and wellness. AI has a lot to offer to students as it can help them learn more effectively and efficiently. By leveraging the power of AI, educators can create a more supportive and nurturing learning environment that helps students feel less stressed and more capable of achieving their academic goals. AI-powered technologies can help educators to create customized learning paths, identify knowledge gaps, and provide targeted feedback to students. AI can also assist teachers in grading assignments and tracking student progress, freeing up their time to focus on teaching and providing individual support. Moreover, AI-powered tools can make education more accessible and inclusive by providing adaptive technologies that can assist learners with disabilities. Overall, AI has the potential to revolutionize the way we teach and learn, making education more efficient, effective, and personalized. AI also plays a crucial role in the finance sector as well. Banks use AI to organize operations for bookkeeping, investing in stocks, and managing properties. AI can react to changes when business is not taking place. AI is used to combat fraud and financial crimes by monitoring behavioral patterns for any abnormal changes or anomalies. The use of AI in applications such as online trading and decision making has changed major economic theories. For example, AI-based buying and selling platforms estimate individualized demand and supply curves and thus enable individualized pricing. AI machines reduce information asymmetry in the market and thus make markets more efficient. Additionally, AI algorithms can analyze vast amounts of data in real time, helping traders make informed decisions and respond to market changes more quickly. Overall, AI is transforming the finance industry by making it more data-driven, efficient, and personalized. The role of AI in trading and investment is becoming increasingly important. With the ability to process vast amounts of data in real time, AI technologies can help investors identify patterns and trends that may not be immediately apparent to human analysts. This can help investors make more informed trading decisions based on real-time data and insights. For example, AI can be used to analyze news and social media feeds, identify market trends, and predict market movements. Additionally, AI can be used to develop trading algorithms that can automatically execute trades based on predefined criteria. This can help investors take advantage of market opportunities in real time without the need for manual intervention. Algorithmic trading has become an increasingly important tool for traders and investors in recent years. By leveraging the power of AI systems, algorithmic trading can make trading decisions at speeds that are orders of magnitude faster than any human could achieve, allowing for millions of trades to be made in a single day without any human intervention. This has led to the growth of high-frequency trading, which is a fast-growing sector in the finance industry. Many banks, funds, and proprietary trading firms now have entire portfolios that are AI managed, and smaller firms are also starting to adopt their own AI systems for automated trading. Automated trading systems can help investors take advantage of market shifts and opportunities in real time, while also minimizing the risk of human error. Overall, AI has the potential to revolutionize trading and investment by providing investors with powerful tools to make more informed and efficient decisions. As with all the sectors discussed so far, AI is playing an important role in the tourism sector as well. It assists in providing personalized recommendations and suggestions to travelers based on their preferences and interests. Additionally, AI helps automate many processes such as booking flights and hotels, optimize pricing strategies, offer real-time recommendations, and manage customer service inquiries. In the context of tourism industry, real-time recommendations could include suggesting nearby attractions, restaurants, or events based on the customer's current location, previous travel history, and other personal preferences. For example, a travel app could use AI algorithms to provide recommendations on activities, sightseeing, and dining options in real time based on a customer's interests and location. These recommendations can help travelers get the most out of their trip and make their experience more enjoyable and personalized. It can also aid in the analysis of customer data and feedback to improve the overall experience for travelers. AI-powered chatbots are also able to provide 24/7 customer service for travelers, helping them in answering their queries, providing them with instant responses such as customized travel itineraries, and helping them to make informed decisions. Customized travel itineraries refer to travel plans that are tailored to the specific needs, preferences, and interests of a traveler. AI is able to generate travel itineraries based on a traveler's budget, travel dates, destination, and other personal preferences such as preferred activities, accommodation, and transportation modes. These travel itineraries can be modified and updated in real time to accommodate changes in travel plans or preferences. Customized travel itineraries can help travelers save time in planning their trip and ensure that they get the most out of their travel experience. AI is also able to help in predicting demand for specific tourist destinations in real time, allowing businesses to prepare accordingly. With AI, the tourism industry can offer a more seamless and personalized experience to travelers and improve their overall satisfaction. AI and other classes such as deep neural networks and convolutional neural networks that are related to each other in some or another way are beneficial in a number of ways. We shall now go through some of the benefits that each group holds. First, we shall go through the advantages of deep neural networks that are a related group to AI. Prior to that, we need to know what deep neural networks really are. So if we want to get a clear understanding of what DNN is in simple terms, then for that DNN should be defined as a class of machine learning algorithms that are a branch of artificial intelligence, or more simply AI. Now without further delay, we shall quickly go through the advantages of deep neural networks. Deep neural networks, or more simply DNN, are beneficial in terms of being versatile, being facilitated with robustness, automated feature extraction, and scalability. DNNs can be used for a wide range of applications, including image and speech recognition, natural language processing, and recommendation systems. DNNs can handle noise and missing data in the input, allowing them to perform effectively in real-world applications. DNNs can automatically extract features from unstructured data, reducing the need for manual feature engineering. DNNs can scale to handle large data sets, making them suitable for big data applications. Now we shall go through the advantages of convolutional neural networks, or more simply CNN, that are a type of deep neural networks, or more simply DNN. CNNs have shown to be very effective at image recognition tasks, often outperforming human experts in some cases. CNNs learn hierarchical representations of images, which means they can capture both low-level and high-level features, such as edges, shapes, and textures. CNNs can be fine-tuned on new datasets with limited data by using pre-trained models. Now coming to AI, that makes up all neural networks mentioned so far, AI can be identified as beneficial in a number of ways. AI is beneficial in terms of efficiency, availability, personalization, consistency, and speed. AI can perform tasks faster and with greater accuracy than humans, which can increase productivity and save time. AI can work around the clock without requiring breaks or time off. AI can analyze data to provide personalized recommendations, products, and services to consumers. AI can consistently perform tasks without being influenced by emotions or fatigue. AI can quickly process and analyze large amounts of data, which can lead to faster decision making. Likewise, being beneficial, AI and the other classes such as deep neural networks and convolutional neural networks that are somewhat related to each other could be disadvantageous in a number of ways at times. So without further delay, let us now move on to the disadvantages of them. We shall now start off with looking at the disadvantages of deep neural networks. DNNs require large amounts of data for training, which can be a challenge for smaller organizations with limited data resources, and large amounts of data for training can be difficult and costly to obtain as well. DNNs require significant amounts of computing power and memory, making them resource intensive and potentially expensive to implement. DNNs can be prone to overfitting, where they become too specialized to the training data and perform poorly on new. Training deep neural networks can be computationally expensive, requiring powerful hardware and a lot of time. The complex structure of deep neural networks can make it difficult to understand how they make decisions or predictions. The theoretical underpinnings of some deep learning algorithms are less clear. Let us now go through the disadvantages of convolutional neural networks. CNNs can be computationally expensive to train, especially if the architecture is deep and complex. CNNs require a large amount of memory to store all the weights and filters due to the number. CNNs can be difficult to interpret, meaning it can be hard to understand why the model is making certain predictions. CNNs typically require a lot of training data to perform as well, which can make them impractical for certain applications where data is limited. Well, now it's time for us to go through the disadvantages of AI that makes up the classes being discussed so far. So let us now start off with going through the disadvantages of AI without further delay. The disadvantage that we are going to address on the first place is that of the AI algorithms being biased. They are biased to the extent of causing unfair outcomes for certain groups, and the factor that is responsible for them to be as biased as they are is none other than the data that they are trained on. Yes, AI algorithms can be biased based on the data they are trained on. That is, if the data that they are trained on is biased in any way, then it can potentially result in them, the AI algorithms, being biased too. For example, if an AI algorithm is trained on historical employment data that contains gender or age biases, the algorithm may perpetuate these biases by unfairly selecting or rejecting candidates based on their gender or age. I hope that this makes it clear for y'all. So let us now move on to the next disadvantage on the list of disadvantages of AI that are going to be addressing here. Moving on to the next disadvantage brings us to the privacy and security risks related to the AI systems. AI systems can collect and use personal and sensitive data, which can raise concerns about privacy and security. At the same time, AI technologies used by organizations can be vulnerable to cyber attacks, putting organizations at risk. One of the main reasons AI system can be vulnerable is through data poisoning attacks. This is where an attacker introduces malicious data into an AI system's training data, which can cause the system to make incorrect decisions. Another issue is adversarial attacks, where an attacker intentionally tries to manipulate an AI model's output to give an incorrect result. Additionally, if AI systems are not secured and updated regularly with the latest security patches, they can be vulnerable to traditional cyber attacks such as denial of service attacks, malware, and phishing attacks. Further going through the disadvantages of AI brings us to other disadvantages of AI that include restrictions in certain characteristic features such as empathy, creativity, accuracy, and complexity. AI systems lack the ability to empathize or understand human emotions, which can be a disadvantage in situations that require human interaction. AI is great at performing tasks that it has been trained for, but it lacks the creativity and intuition of humans. AI algorithms can make mistakes, particularly when they are trained on insufficient or biased data. AI technologies can be very complex, which can make them difficult to understand and manage. This can create challenges for organizations that lack the expertise to properly implement and maintain these technologies. Other disadvantages apart from all that have been discussed so far include dependency risks, high cost risks, and ethical concerns. Dependency risks arise when we become more dependent on AI technologies as a result of becoming more reliant on them, that it turns out to be problematic or a cause of concern when they fail or are compromised in some way. High cost risks emerge when particularly small businesses or organizations with limited resources implement AI technologies that are potentially expensive for them. Ethical concerns related with the use of AI is that as AI technologies become more advanced, there are these concerns around issues like privacy, surveillance, and the potential for AI to be used for malicious purposes. Terrorists, criminals, and rogue states may use other forms of weaponized AI, such as advanced digital warfare and lethal autonomous weapons. Many countries are researching battlefield robots, and machine learning AI can design toxic molecules in a very short time. Although AI and the other classes such as deep neural networks and convolutional neural networks are beneficial at most times, they are disadvantageous at certain instances. Therefore, we need to find ways to tackle the challenges faced during the utilizations of AI and the other classes, such as deep neural networks and convolutional neural networks, for the benefit of our society. We shall discuss further regarding the ways in future videos. Until then, signing off. A commoner. Thank you.